Hello everyone, welcome to Math 465, Introduction to Differential Geometry. My name is Mark Hughes, I'll be your instructor. And first of all, I want to start off by apologizing that the first two lectures will be recorded lectures. I know this is not the ideal way to start a course. I am recording these lectures from South Africa, where I was invited to give a talk at a research conference. I didn't entirely realize when I accepted the invitation to come speak at this conference, I didn't entirely realize that this would be the first 2 days of classes that I'd be missing. Normally we start, I think, before Labor Day. Maybe I'm just making that up in my head. So I thought this was sort of going to be the second week of classes, which is also not a great time to miss. But I apologize that the first two lectures will be online. But I will be back on, I guess, September 11th, and we'll be teaching in person from then on. I will do my best to go through all the sort of the important information about the course to give you an idea of what the course will look like. This is the first time I've taught this course. It is also a small class, so I believe we have 7 or 8 students currently. And because of that, we do have some flexibility in the class. And so if you have any questions on how the class will run or exactly things like homework schedule, stuff like that, feel free to reach out and ask me. I can meet online if you'd like to this first week. If you'd like to meet over Zoom, I'm happy to meet. Just send me an email. Otherwise, we will, I'm also happy to respond to emails. So feel free to reach out with any questions you have, especially this first week while I'm away. I know that sometimes on the first day of class, people have questions, and it's nice to be able to ask the instructor those questions. But since I won't be there, I'm of course will be more than happy to respond over email or in any way that you need to get in touch with me. So. Just a few details about the course. I do have some, the best way to get a hold of me is just by emailing me. I am except on days when I'm like actually in an airplane traveling, I do check my email fairly frequently. Sometimes I can't respond, especially if it's a more detailed question. I can't respond right away, but I will try my best to respond to those emails. I do have office hours scheduled Monday, Wednesday, Friday. I tried to pick times that were I tried to pick sort of a variety of times so that, if you have classes during one of my office hours, hopefully you'll be able to make it on a different day. Of course, if none of these office hours work for you, or if you need to see me on a day where I don't have a scheduled office hours, you are always welcome to send me an email and try and set up an appointment. Reach out to set up an appointment. Our class location was changed. I think fairly recently. We'll be in TMCB 301, so on the 3rd floor of the Talmadge building, and we'll be meeting from 11 to 11:50 every day. The textbook we'll be using is Differential Geometry of Curves and Surfaces, the 2nd edition by DeCarmo, and I've got a little picture of it down here. So this is what the book looks like. There is an older edition of the book. I don't know how much has changed between the two editions. I also have the older edition. I think the newer edition is not too expensive. I think it's a Dover book. I'm actually going to look it up right now just to see. I guess maybe I don't need to because probably a lot of you have bought it. But I think, now why isn't Amazon coming up here? On Amazon, the revised edition comes in at paperback between $10.58 and $40. So I guess depending if you're getting it new. It's a good book. It's been used sort of for many years. It's sort of the standard, I'd say, for a course like this. There are some other books and notes you can find online that would give you maybe a slightly different perspective. So if for whatever reason you don't like the writing style or whatever, you're also welcome to. I have a few other books that I could recommend. And largely they cover the same material. Most of this material is fairly standard in a course like this. So you can find other references, and I can give you recommendations on other references if you'd like. So in the course, Math 314 and Math 341 are prerequisites. This is sort of, a lot of what we do will sort of be extending what you see in multivariable calculus. This is kind of a cool course because, so I teach differential topology, which is a 600 level class. And I also teach the graduate version of differential geometry, which is a slightly more abstract version of this. The nice thing about this class is that we will get to see a lot of concepts that show up in differential geometry and graduate level differential. I forget if I said differential. We'll see concepts that show up in graduate level differential geometry and differential topology, but we'll mostly be focusing on it from a perspective of studying curves and surfaces. So it's a lot more concrete of a setting to work in, but a lot of the concepts you'll see in those important concepts that you'll see in higher level classes will still show up in the setting that we're working in. So if you do plan to take more differential geometry or differential topology, this is sort of a great course to get your feet wet and to sort of familiarize yourself with some ideas. And we'll definitely see some cool stuff here. We will have roughly weekly homework assignments. So typically I try and pick a day when we'll assign homework, and so maybe I'll assign it on a Monday and it'll be due the next Monday, something like that. Sometimes the way the material lines up in a course, in an upper level course, it's kind of, it might make sense, maybe we need to cover just the end of a section, and so maybe homework one week might be assigned on Wednesday or whatever. I'm somewhat flexible as to when homework is assigned and when it is due. In the past, I've had students who've said, oh, we have our, probability homework that's due on Fridays. Could we have our homework due on Wednesdays instead? And generally, I'm okay with that. So if there's a day that sort of works best to have your homework due, that will be fantastic. So we will have midterm exams. We will have classroom presentations, and I'll say a little bit more about that when I get to class. Those will be sort of a little bit later on. We will have a midterm exam and a final exam, and then here's roughly the breakdown of the grade, the final grade. So hopefully this kind of gives you the idea of what the course will look like. Like I said, there is some flexibility. Oh, and here's some standard stuff that we need to put in about the honor code, preventing and responding to sexual misconduct, and student disability. So I think this is all sort of stuff you'll see in most syllabi nowadays. So if you have any questions about any of this, I'm happy to chat about it. Like I said, we do have some flexibility in the course, so we want to find something that works for all of us. So feel free to let me know if there's certain just whatever, if there's certain things that you need to let me know. So normally at this point I'd pause to ask if there's any questions, since we are all separated by, I don't know, thousands and thousands of miles. I don't have any questions to answer right away, so I will jump into the material. I'll keep this a little bit shorter than maybe a full lecture, just because I know sometimes when you're listening to an online lecture, you need to pause things, read things, stuff like that. So, and normally in a class we'd have questions, so it would kind of slow us down. So I won't go for a full 50 minutes here, but I do want to sort of dive into the material. Let me give myself some lines to work with. College rule, the best rule. And let's go ahead and let's get started. So the first actually two sections are somewhat short sections, but they're kind of setting the stage for a lot of what we'll talk about. So let's get started here. So the first section is section 1.2. The section 1.1, if you're wondering what 1.1 is, it's just sort of an introduction to the chapter. So it doesn't have any sort of real meaty content there. So we'll start with 1.2. And this section is all about parametrized curves. All right. So first of all, we want to just sort of set some notation out. We're going to let R3 be sort of what you'd expect it to be. It's just three-dimensional Euclidean space. Okay, and this will be the primary setting of where we work in this class. Okay, a lot of the concepts we talk about will generalize elsewhere, but this is sort of the nice place to start because it's concrete. We can sort of visualize what's going on here. We can draw nice pictures, and so that's a good place to start. Whenever I draw I, at least initially, this is just going to be some open interval. Okay, and in particular, I don't care if A could be negative infinity and B could be positive infinity. Okay, so So this is an open interval. It could, on either side, it could go off to infinity. All we require is it's some open interval. It could be, infinite, half infinite. It could be really any open interval that we pick. Okay. So if we consider, we're going to consider a class of functions. So any function, say alpha, from an open interval into R3, well, a function from an interval into R3 is going to take a real value. Let's see if I can pick my laser pointer here. There we go. Is going to take a real value in this open interval, and it's going to send it to a 3-tuple in R3. So it's going to send it to a point in R3. And so what that means is that this function can be sort of decomposed as 3 functions. So x of t, y of t, and z of t. Okay, where this is doing exactly what you think it's doing. This first function is just a real valued function on the interval, and it's just going to tell you what the x-coordinate is of the image of the point t. So we take a point t, we plug it into this function. This function is going to send it to a point in R3, and any point in R3 has 3 coordinates. So we're just essentially spelling out these 3 coordinates separately. Okay. And so really what these x, y, and z's are, x, y, and z are all functions from the open interval into R. Okay. So these functions give us sort of a convenient way to describe this alpha. And so we're going to call these we'll call xt, yt, and zt the component functions of alpha. Okay, so give us a nice way to describe the function alpha, and we'll also call t the parameter of alpha. Okay, so we've got our component functions, which are essentially just telling us the x, y, z coordinates, and then the parameter is the thing that we're inputting in there. That gave me an arrow. I didn't want an arrow. I wanted just a straight line. Okay. All right. So the nice thing about having real valued component functions, each of these is just a function from an interval into the reals. The nice thing about having a function from an interval into the reals is we know how to take derivatives of such things. So since the component functions are real valued, we can try, I guess I should put the 2, we can try to take their derivatives. Oh, I should mention, in general, I'm going to be writing on the whiteboard or the blackboard in class. I guess we're in 301, so we have a whiteboard. I do make my lecture notes available online. Everything for the class will be posted to Learning Suite. So if you go into Learning Suite, either under the course content tab or under the announcements, you should see an announcement or a content page with a link to the lecture notes. So you can find sort of a copy of these lecture notes online. And I'll sort of upload them as I create them. I haven't taught this course before, so I haven't created all the lecture notes yet. But occasionally, if there's an error or a correction that needs to be made, I will correct it in my notes, and then I'll usually upload. I will always try to do this. Upload a corrected version to Google Drive or to the link that you see in Learning Suite. So check back there often. I'll be updating things throughout the semester. So back to the task at hand. Since the component functions are real valued, we can try and take the derivatives. So for example, we can try and take the derivative of xt, which we'll sometimes just denote by x prime or dx by dt. And of course, this is just the limit as h goes to 0 of x of t plus h minus x of t over h. Okay. Now, of course, this derivative may or may not exist. x might be discontinuous. Remember, we didn't say anything about the function alpha. We just said it's a function. So it could be a truly, truly horrendous function with many, many discontinuities, and it could be differentiable nowhere. Okay? Of course, those are really weird things. We don't want to deal with that. So we're going to focus on differentiable functions alpha. Okay? So now, one sort of important thing, distinction with how the book talks about this and how we'll talk about this in this course. So we'll call a function f, a real valued function f, differentiable if its derivatives exist, its derivatives of all orders exist and are continuous. Okay, so for example, we want the, if when we say f is differentiable, we're saying that df by dt exists, the second derivative of f by t exists, the third derivative of f by t exists, etc. Okay, so we want all the derivatives to exist and we want them to be continuous. And I suppose if you consider the, f to be the zeroth derivative, then we also want it to be continuous. But really, I mean, there's, we don't, you could just say that we want all the derivatives to exist, and that sort of implies continuity. But essentially, we want to be able to differentiate this thing infinitely many times, or as many times as we want. Okay, and when I say they exist and are continuous, I really want them to exist and be continuous on the entire interval. Okay. So sometimes someone will say differentiable function, and all they really are implying is that they want to be able to take the derivative a single time. Here and in the book, when we say differentiable, we mean we want to take the derivative infinitely many times. We want to be able to take the derivative infinitely many times. Okay, so this is sometimes called infinitely differentiable. Sometimes people will call it C infinity, or they'll call it smooth. Okay, so if you're reading a book and you come across any of these terms, really they're talking about sort of being infinitely differentiable, like we're talking about. Although the book that we're using will only call it differentiable, and that's when they say differentiable, they mean infinitely differentiable. Okay. So this brings us to our first definition. A parametrized differentiable curve okay, so a parametrized differentiable curve is a function of the form alpha, which maps an open interval into R3, whose component functions are all differentiable. Okay, so essentially it's one of these functions that we were talking about above that looks essentially like this, but what we're requiring is requiring each of these functions here to be differentiable, to be infinitely differentiable. Okay. Now, it actually, the fact that we're mapping into R3, I mean, you could just as easily be mapping into R2 or be mapping into R7 or whatever, and I would still call that a parametrized differentiable curve. However, in the book, we mostly focus on R3, although they do give some examples of curves into R2. All the definitions work, so there's nothing to be worried about. We're just sort of stating this definition in terms of R3, but it could be in any dimension, really. We just have we just have more or less component functions to check differentiability for. All right, any questions? I always hate how you can't ask questions. So when I come back to class on Monday, we will take some time at the beginning of class just to make sure if there were any questions that came up, you have a chance to ask them. Also, of course, if you have questions and you want to just shoot me an email, that is also very okay as well. Okay. So, because you are all such good students and obviously have no questions, because no one is speaking up, I can't hear any questions being asked. I'm just going to continue right on. So if alpha t if alpha t is a parametrized differentiable curve. Oh, and by the way, I won't always say okay. I won't always say parametrized differentiable curve. If I just say the word curve from now on, you can assume, unless otherwise stated, that it is a parametrized differentiable curve. We'll add some other qualifiers on it in the next section, but it will be a little cumbersome to say parametrized differentiable curve every time I want to talk about something like this. So I will often just say curve, and you know that it's differentiable and parametrized. So suppose we have one of these curves, then since we know that the components are all differentiable, we can take the derivative of all of them. Okay, we can take the derivative of all of them, and we're going to call the function that you get when you take the derivative of all of these things, we're going to call that alpha prime. Okay. Now, of course, we can take the derivative of these things at any point that we want on the interval I. And so that means that, at different points on the interval, we're going to get different derivatives. But what you get is this thing here will always be a three-dimensional vector. It'll always be a point in R3. Okay? And so we're going to call this the tangent vector. Okay? Sometimes we call it the velocity vector. Of alpha at the point t. Well, maybe I'll just put a period there. Okay, we call alpha of I. So if I take my whole interval and I plug it into alpha, in other words, this is just the image of I under alpha. This is called the trace of alpha. Okay? So there's oftentimes it's sort of tempting to think about the function and the image of the function as sort of being the same thing, especially in a situation like this with a curve, but it's not entirely correct. Okay, and so for example, maybe I'll jump to this example first. I'm kind of, two distinct curves can have the same trace. So for example, well, it shouldn't be too hard to think of an example. We could do, I wanted to try and think of a better or different example than what they gave in the book. So in general, I'll try and have different examples to sort of augment what the book says. I'm just scanning through my notes. Maybe I didn't have a separate example of this. So maybe I'm deviating from my notes a little. Oh, yeah. So well, I'll just do this example. So alpha, if we want to curve into R3, we could just do alpha t is equal to cosine t sine t comma t, or beta t is equal to cosine 2t, sine 2t, and 2t. Okay, and we'll actually, I guess we'll come back to this and talk about exactly what this shape is here, what this curve looks like. But essentially, by replacing the parameter t with 2 times t, essentially all we're doing is we're traveling along the curve twice as fast. Okay, so the image of these two functions will be the same. Okay, the image of these two parametrized differential curves will be the same, so they'll have the same trace, is what we would say. These are two different functions. And so we should, I mean, oftentimes we can sort of think of a curve and its trace as being sort of the same information, but sometimes it is important to sort of distinguish that the trace, you can have the same trace and have two different curves. So you got to be a little bit careful. So maybe let's look at a few examples now. Let's look at this example here first, okay? Oops. I keep activating the recorder thing here. So let's look at this example here first. What does this look like? And when I say what does this look like, I mean what does the trace of alpha look like? Okay, if we were to sort of plot this thing out, what would it look like? So I think all of you have taken Math 314, which I think should give you, I've never taught 314, but I think it should give you a little bit of sort of intuition with how with how to view things like this. But if not, we'll kind of review it. So the first thing that I like to do is I always what might be helpful is sort of ignoring one of the components. It's nice to sort of maybe see what's going on in like the XY direction. So we can kind of, first of all, we can actually just sort of look at what happens in each of the directions separately. So if we sort of have, if each of these is like, if this is like x, t, y, t, and z, t, we can try to figure out what this looks like. So cosine, well, we all know what the cosine function looks like. Looks something like this, right? I think I'm drawing it right. The sine function looks something like this. And the function just t, z equals t, just looks like this. Okay? So we have our two functions. Now we want to sort of see when we combine each of these coordinate functions, we want to sort of convince ourselves what this looks like in three-dimensional space. And the pictures, once you start going up to three-dimensional space, they don't look quite as nice as in two-dimensional space. Or actually, let's do one intermediate step first. Let's sort of combine, let's combine the x and the y first. So this is my y dimension, this is my x dimension. Well, as if we start off at 0, if we start off with the 0 parameter, then our x is at 1 and our y is at 0. So we're right here smack in the middle, or smack here, okay? Then as t starts to increase, notice that our x component is going to start decreasing, whereas our y component starts increasing. So our x component starts decreasing while our y component increases. And of course, this is something we've seen before, just cos t sine t. If we travel this around, it's just going to give us the unit circle. Okay? So we get the unit circle in the xy direction. Now if we want to make this, fancier, right? Because you're paying good tuition money, right? You want to make this fancy so you can show it off as a party trick, right? So if we sort of factor now in the z direction, what we're going to see here is as t sort of increases, what we're going to see is we're going to see a unit circle, okay? Then this unit circle is going to sort of trace out in the xy direction, okay? So this is y and this is z here. So in the xy direction, we're just going to see this unit circle trace out. And once we get to 2 pi, we're just going to go back around again and again and again, okay? So in the xy direction, we're just going to get this circle that's traced out over and over again. In the z direction, however, we're just increasing at a linear pace. So what this is going to look like is we're going to see a bunch of circles that we're going to trace around, but our z direction is going to keep increasing as we trace around those circles. So we're going to get a corkscrew type thing here, okay? Or a helix or something that wraps around in the counterclockwise direction as it moves up, okay? So that's what that looks like. And so if you don't feel comfortable, or, you know, it's good to get some practice at, you know, when you see a function like this. This is obviously kind of an easier one, but it's there are some like computer algebra software that'll help you graph it if you want, or there's other ways to try to visualize it. But it's good to sort of be able to sort of take a function like this and sort of learn how to visualize it, okay? Now, of course, if we do this instead, we're going to get the same thing, but instead of sort of traveling at, you know, say unit speed in this direction, whatever, we're going to be traveling at twice that speed, okay? Because we've just sort of replaced our parameter with 2 times t. All right, let's go to another example. Oops, let me make that blue again. Here's kind of an interesting example, and this will be important in what follows. So this is just going to be a curve into R2. This is going to be alpha, which maps the entire real interval into R2, given by alpha t is equal to t cubed t squared. Okay, so what does that look like? Well, in the x direction, t cubed looks like this. And in the y direction, so if this is x and this is t, in the y direction, we have something like this. So this is our y coordinate, and this is our t coordinate. So when we combine the x and the y together, what's going to happen is our x coordinate is increasing really fast away from 0. And then it's going to start decreasing, and it's going to start slowing down as we approach 0, and then it's going to start speeding up again and moving away. Likewise, our y coordinate is decreasing as it approaches 0, and then sort of starts increasing again. So it might be kind of hard to see, but essentially we're going to see something like this. Okay? So this is x and this is y. And it's kind of a little weird because you see, if you were to plot this in Mathematica or some other algebra system or plotting software, you're going to see that it has what looks like a cusp here, a sharp dent there, okay? And so when we think of differentiable functions, we think of things that are smooth, right? And so to see sort of a cusp like this, it should be a little disconcerting because it looks like this thing is not smooth. It's not differentiable. Okay. However, this is differentiable. So this function, the curve alpha given by this, is differentiable. Okay. The key thing is, though, is our derivative is going to be 3t squared 2t, and at t equals 0, alpha prime of 0 is just 0, 0. Okay? So notice that this tangent vector, this tangent or velocity vector, whatever you want to call it, this function, this curve is differentiable. It's completely differentiable. It's nice. But what happens at the origin is that tangent vector vanishes. And so essentially that's what allows us to have this sharp point here, is that the tangent vector has vanished. And so we get a curve that doesn't look smooth, even though it is parametrized and differentiable. So the way that I think of it is sort of we have this tangent vector, and the tangent vector sort of tells us our velocity. And so essentially we're traveling along this curve here really, really fast initially, but as we start to approach 0, our velocity slows down. And it slows down and slows down and slows down until we arrive here at the cusp point, And at that very instant, it stops to 0, but then restarts again going in this direction, after which it speeds up. Okay? So it's differentiable, but what's really going on here is that we're not making any sharp turns. We're only sort of really slowly slowing down to a stop, and then in that instant we're turning and starting back up again. Okay, so there's no sort of sharp turns that we have to worry about. It just sort of is what's going on there. Okay. So let's talk about let's see how we doing on time. Okay, maybe let's do just 2 more quick examples. This is an example from the book, and then I'll do an example not from the book. So the curve alpha of t, comma, absolute value of t is not differentiable because the absolute value of t function is not differentiable. Okay. Which is maybe a little weird, because if you look at the plot of this, this is just our absolute value graph. And clearly that doesn't look differentiable at the origin, but again, neither did this thing here, right? It doesn't look any worse than this one is, but it is worse, okay? So this is not a parametrized differentiable curve. All right, so, all right. So let's now talk about this tangent vector field. So we call this the tangent vector field. Why do we call it a tangent vector field? Okay, so let's just make a side note here. So why do we call alpha t prime why do we call this a tangent vector to alpha? Okay, I mean we sort of have a concept of tangent from Calc 1, right? And so I think intuitively we know that the vector that we get here should be sort of the vector that points in the same direction as the curve does at that instant. But why is that true? So suppose, let's just talk about sort of a simple example. So suppose we have a function, say f of x, okay? And so we can, so we have the graph of the function y equals f of x can be written as a parametrized differentiable curve by, so essentially we want, what we want to do is we want to write down, so let's draw the picture here. If I draw the graph of this function, something like this, this is y is equal to f of x. That looks like a curve to me. It looks like it's a one-dimensional thing. And so hopefully we can parameterize it as a curve, as a parameterized differentiable curve. And it turns out we can. All we're going to do is we're going to let x be the parameter t. And then if x is equal to t, then y, which is supposed to be equal to f of x, that should just be equal to f of t. F of x, which is f of t. Okay? So this parametrized differentiable curve is going to look like, is going to give us exactly this graph there. Okay? So now let's pick a point. Say t naught. The tangent vector so the tangent vector to alpha of t at t is, so if we take, so if alpha is just t comma f of t, then alpha prime of t is going to be the derivative of t with respect to t, which is 1, and the derivative of f of t with respect to t is just f prime of t. Okay, and so hence at t naught, alpha prime of t naught is equal to 1 comma f prime of t naught. All right? And so if we look at the vector we get here, right, this is really just a vector. It's really just a vector with, I guess I didn't need to draw it that big, but it's a vector you step one step in the x direction and you step f prime of t naught in the y direction. So it's this vector here, right? And so the important thing is that this vector has slope f prime of t naught. Okay, so if we were to take this vector and we were to draw it, now my picture is going to change a bit because I don't remember what my first picture looked like, and I actually didn't really like it that much, so I'm going to draw a slightly nicer picture. If we were to look at the graph of our function, something like this, and say the point that we've picked here is like, say the point we've picked, let's do it right here. Say this is t naught. Okay, well, the derivative, this derivative vector is right here, so that's 1 f prime of t naught. Sorry, my writing didn't plan that out well enough there. So this is f prime of t naught. Okay, so notice this, the slope of this vector, right? This vector has slope f prime of t naught, which is exactly the slope of the curve at this point. Okay, so if we took this purple vector and we translated it, the idea is that this purple vector should be the tangent vector to the curve at that point. And I don't know that I've drawn it perfectly, but you get the idea, right? And so when you compute this tangent vector, okay, notice the vector you get is always going to be, the vector you get is going to be either in a point in R3 or a point in R2, right? And if you take that point in R2 and you connect it to the origin with a line, that's going to give you some arrow that has some slope, right, with respect to the x-coordinate. And that arrow that you get, it's not going to be tangent. It's not going to be tangent to the curve, right? Like this arrow that we get is not tangent to the curve. But if you translate it to the appropriate place, then it will be tangent to the curve. Okay. So these tangent vectors, like we think of them as vectors coming out of the origin, and so they don't naturally sort of live on the curve. But if you translate them to the correct spot on the curve, they will be tangent to the curve. Okay, and so oftentimes we will draw the tangent vector in, and we'll draw it sort of at the various places on the curve. Okay, and the understanding is that these vectors are really vectors that we've obtained by translating from the origin, by taking the derivative and translating from the origin. Okay. All right, so I've been going for about 40 minutes, which is probably about this amount of content I would have gotten through class if we had questions and stuff. So I'm going to probably stop here. I will take a quick break and then start recording the Friday lecture. If you are if you just love math and love the sound of watching me listening to me draw math on my iPad, then you can go ahead and watch the Friday lecture right away. Otherwise, you can hang on and watch it on Friday. But again, feel free to reach out if you have any questions. Again, I apologize. This is an online lecture, which is not ideal. But hopefully if you have questions, you can either ask them to me over email, over Zoom, or we can talk about them when we get back on Monday.